back to one of my favorite cities, actually. I spent here two of the best years of my life with Professor Jeffrey Austin in the Department of Chemistry. And I haven't been here for more than 10 years now. So it is actually great to be back. Well, I'm going to talk to you about this, but first let me just show you briefly where I am. This is the Institute of Material Science of Seville, that belongs to the Spanish Research Council and the University of Seville. And this is where we are located, in the very south of Europe, and it's a part actually of Europe with many hours of sun per year. So there's a lot of solar activity both in companies and in research in this part. These are pictures of the city where I live. It's a beautiful city. I'm not from there, so it's not vanity, but I highly recommend it to visit. So this is the outline of the project. I'm going to give you a very brief introduction to photonics for photovoltaics, and then I will talk about two types of third generation solar cells. I will not cover all of them in principle, basically because not in all of them it's possible to do actually photonics. In these two that I'm going to present, solar cells and perovskite solar cells, it is actually possible. So let me start by stating why we need, or why it's interesting to have an optical design in general in photovoltaics, and the relevance of optical design in photovoltaics is related to a very basic and fundamental principle in the field. On the one hand, we are very interested in absorbing as much light as possible, right? And in order to do that, in principle, what I want is to have a material as thick as it is needed, so I can absorb all that. Right? On the other hand, I have to connect the photocarrier that I'm generating. And in order to do that, I need a material as thin as possible, so the carrier does not have to travel too much to get to the metal point. And it is in this balance, in this compromise, where the optical design becomes relevant. It's pretty simple if you put it this way. If I want to have maximum absorption in the minimum thickness possible, I have to try to shape my material, or design my device in general, so that I get the maximum absorption in the minimum thickness possible. Right? Well, so what are the different strategies that one can follow to trap light inside your device, to harvest more light? Well, a very basic one that is common to most solar devices is just to reduce the electron reflection. This is typically achieved by creating some sort of hyper-reflective coating in your device, and this can be made with very simple or very sophisticated actually designs too. I will not be talking about that today, although it's also part of the research we do in Seville. The second strategy is to increase the optical path. So basically, the idea would be that when my light reaches the device, it is somehow reflecting inside the absorbing material, so I have a longer path inside my active material, and I have a higher probability of getting absorbed, for the photon to be absorbed. The third one is actually a little bit more sophisticated, which is to increase the time of flight inside my material. That means that maybe I can shape my material so my light will travel to slow modes, so my light will travel slowly, and that also increases the interaction between the radiation and matter, and therefore the probability of absorption again. And finally, another strategy that is very popular these days is to increase the optical field, which is related to the use of plasmonic nanostructures inside the solar cells. Well, these are the strategies, and the materials that we need to achieve these are very different kinds. So it's quite common in the field of photovoltaics to use texture surfaces. Texture surfaces can be used to achieve anti-reflection, can be used to increase the optical path, because I can have, let's say I have a texture surface that doesn't have order, right? So I will get diffuse scattering that will increase the optical path of my light inside the device, but I can have another texture surface and I will get diffraction. And in that way, I will also deflect my mass with an angle, and I will increase the optical path inside my device. Actually, if the texture surface is metallic, I can also have near optical field enhancement effect. I can use also plasmonic nanostructures, and by that I can invest in nanoparticles, right? Or arrangements of nanoparticles. In that, with these sort of materials, I can enhance my near optical field, and I can also get isotropic scattering, which can be also interesting. I'm increasing it by this, by doing this also the optical path of light inside. Photonic crystals that offer us a wide variety of phenomena that can be exploited to improve the absorption, ranging from slow light propagation that I mentioned before to increased optical path through refraction or simply specular reflection, as well as this different type of enhanced near optical field that is basically related to the fact that I can have point spots inside photonic crystal if I look at the way in which the magnetic field distributes inside. Finally, disordered bulk material. So I can basically have a material in which I have introduced disorder in the units of refraction inside, and I can get multiple scattering that will also increase the optical path of light inside. Well, this is a very basic description of the strategies and the material aspects of light trapping that can be used in solar cells. And I will start now by trying to apply all these different concepts to the solar cells that I will present, which are dye-sensitized solar cells. So I think part of the audience might be familiar with this, but I'm just going to give a brief introduction to it. So a dye-sensitized solar cell is solar to electric energy conversion device that is based on a film that can be about a few micron thick, made of nanocrystalline titanium. So this film of nanocrystalline titanium is going to have a very large surface area. And on the surface of these crystals, a dye, which is represented by these violet dots here, is absorbed, and this dye will have the function of absorbing solar light and transferring this electron from the excited state to the conduction band of this kind of a scaffold, which is this titanium oxide. And this is what is represented in this very basic scheme, right? So sunlight excites electrons to these higher energy states, then transfer to conduction band of the titanium oxide. It travels through there and reaches the metal contact, and well, the circuit is closed by having obviously a counter electrode and a redox electrolyte, whose function is to capture the electron in the counter electrode and take it to the dye, so it is regenerated, and in this way we have the closed circuit. Well, having said this, which is a very basic description of the dye-sensitized cell, one of the interesting added values of this cell when it was originally proposed was can be seen here. It is semi-transparent, right? So this is a cell that the dyes that are commonly employed. There's a certain part of the solar spectrum that could go. Right? Obviously, this is not good. We would prefer to absorb everything and to have a black material, but this is how it is in the field. So this is the structure that you see. You take one of these cells and look at it in the microscope, and scanning electron microscope. This is a cross section. So this is basically glass. This is FTO, which is the transparent conductive oxide that we use as a metal contact. And this is the nanocrystalline titanium. That as raining as you may look here, it is from the optical point of view, homogeneous material, so it's completely transparent. This transparency actually allows you to do things like this. This is a picture of the, I think it has been not too long ago inaugurated conference center in Relevance, and all these windows are covered by these dye-sensitized solar cells using different dyes. Right? So you can. This is an example of integration of photovoltaic buildings, and it also highlights why it is interesting to have transparency. However, having said that, most of the highly efficient devices that people have developed in obviously all record cells, what has been done is to kill that transparency, to get rid of it, because we want to absorb more light, and we don't want light just to go through the cell and not contribute to the generation of electricity. So there are two main approaches that have been used in the field to increase light absorption, and both of them are based on diffuse scattering. Right? So this is just to highlight that this is a field in which all record cells have made use of optical design. Maybe a very, well, not too basic, but a basic one. But this is the design that has been employed for most record cells, in which the diffuse scattering layer, made of large titanium particles, is used in the back of the electrode to provide us with this diffuse reflection. So basically, photons that haven't been absorbed in a first pass through the cell are reflected in a oblique angle, so we have increased a lot of probability of absorption. Right? And this approach works very well. Another one is to introduce diffuse scattering inside the non-crystalline titanium field itself, right? Just as it is represented here, and these lines that you see, well, are describing a very obvious approach. What happens to a photon, right? That when it goes into a system like that, it undergoes a series of scattering events. The optical path is then larger, and the probability of absorption is also larger. Well, there is something important that you have to consider every time that you change the optical design of your device. Obviously, the main motivation is always to improve the optical absorption. So we want to increase light harvesting. However, the optical design affects something else, which is the collection efficiency. And I'm going to show you here. There's a very simple equation. So this is our incident photon to current efficiency, or collected electron. It's basically our external quantum efficiency. And it depends on the product of a few efficiencies. This is light harvesting, or absorption. These are injection and regeneration efficiencies, which are out of the problem in terms of the optical design. Right? And there's this other one, which is the collection efficiency. So the collection efficiency, basically what it's accounting for is once I have injected an electron in the conduction band of titanium oxide, the electron has to travel, okay, and reach the electron. And how efficiently this happens, right, is represented here. Well, that depends on something that is, this is the equation for the collection efficiency, and as you can see, it depends on this function, which is the electron generation function. The way it can be called for the voltage, which is nothing else than the absorption profile. So this is what is the absorption profile inside your field. And this is another way in which your optical design is modifying your the performance of your cell, not only by increasing light harvesting, but also by changing the position inside the device in which the carriers are generated. Is this relevant? Well, it is actually, although not always, and this is exactly what I'm going to say next. If I compare these two, if I compare these two designs, both of them based on diffuse scattering, and just please notice that I will use these black lines always to represent the bare cell without the transparent cell, and this dashed red line and blue dotted line to represent the data for these two designs here. So basically, if I check the absorption, light harvesting, with a design like this, with diffuse scattering particles inside my field, what I get is a better absorption. You can be seeing this light harvesting efficiency. And I get a much better one if I use a diffuse scattering layer in the back. Right? So this is basically the key to the use of this design over this one in a field, just because I get more light. But if you look at the absorption profile, so this is the energy generation function for 3 different wavelengths, right? In the red, in the green, in the blue. You see that, well, for this case here, I get the generation, the electron generation function that I expected, following number very low, right? So something weird. However, when I have this design here, you can see that the maximum absorption takes place closer to the metal contact. So in principle, with this design, I'm favoring electron collection because I'm increasing the absorption closer to magnetic contact. On the other hand, in the case of the diffuse scattering layer in the back, I have a very different electron generation function. Right? So in principle, if I have a look at this, the collection is better for this one. I'm favoring collection, but the absorption is better with this design. Right? So what is it going to determine that one design is better over the other? Well, basically, it's going to be a function of the electron diffusion length. In systems in which I have a small electron diffusion length, which is this L here, right? And here I'm giving you data for 7 micron solar cells, 7 micron big solar cells. So if I have a system with a 1 micron electron diffusion length, the optimal system is the one that has particles inside the field, and not this one. Right? Because it is very important to have an interesting collection. Electrons that are generated a little bit far from the metal contact will not be collected. However, if I have larger electron diffusion length, the right system, the right optical design is this one. In the field of light-sensitized solar cells, the electron diffusion lengths are larger than this one. So in principle, it doesn't matter. So it's always this one the best one. Right? It has always been. But not for all light-sensitized solar cells. For instance, for flexible solar cells, flexible light-sensitized solar cells, the electron diffusion lengths are much shorter. Because you cannot synchronize, you have no absolute connectivity in the field. So in those cases, it might be better actually to use this design. Right? So it depends a lot on, you need to know how is the diffusion of your carriers inside your cell to decide which is your optimal optical design. It's not only light absorption. Right. What I've been showing you are all the calculations that we do considering that we have isotropic scattering. Why? Because most of the commercial phases that you can obtain in the field are actually polyhedral particles with very wide distribution of sizes. So you cannot have a true control over the scattering event when that is taken. However, if you can work with the spherical scattering centers, like the ones I'm considering in this work, then you have a very precise control over the way in which light is scattered when there is one scattering event. And what we did here was to compare the efficiency that you would get when you use dielectric particles or with titanium oxide particles, when you just make holes inside the film and let them be filled with electrolyte, or when you use gold or silver particles. We did that because there were quite a few works trying to introduce these metal nanoparticles to take advantage of plasmonic effects. And obviously in all papers people observed some sort of advantage and some sort of increase of efficiency, but there was no systematic study of the relative or systematic comparison between the effects of different types of particles. So what we found is basically that there is no point in principle in using metallic particles in light-sensitized if you can use dielectric particles or even holes in the system. The efficiencies that you're going to get are always much larger with dielectric particles, and also the tolerance is fantastic. If you look at these graphs here, so these are just map of efficiencies versus the concentration of particles and the size of the particles. There are huge regions in which you can get very high efficiency. So you don't have to be extremely careful. You can get a very good result just by using particles of different sizes and in a wide range of concentrations. This is not the case for metal particles. If you want to improve your efficiency using metal particles, first, the improvement is lower. And second, look at the x-axis here. So your concentrations are much smaller. And you have, if you go a little bit above these values, it will start increasing the efficiency of your system. The reason is because metal particles are competing with the dye in terms of light absorption. So once you introduce a metal particle, it's true you have a near field enhancement effect. You have also a spectral scattering. These two factors are interesting, but at the same time you have introduced in the system a very strong, potentially very strong parasitic absorption. This is why you cannot go to very large concentrations of metal particles in your system there, or you will start getting an increase in the optical absorption. So the contrast, the effect opposite to the one we want to get. Well, with all this analysis, we started actually a collaboration with a group in Korea, a group of Ninja, who is actually an expert in flexible disolar cells, and we have been designing the optics of the cell so we can get a very high efficiency on plastic substrates. So we got a very interesting result. Actually, we got a 8.6% efficiency with plastic substrate, which is one of the highest, I think it's the highest value reported for plastic substrate for a disolar cell. 7.8 for a fully flexible device like the one you see here, which is actually close to the record, world record of fully flexible devices, that is actually 8%. And all this development, was a gradual development, was based on optimizing the scattering inside the solar cell. Well, so as I said before, since in this field we wanted to improve the light absorption at the expense, because I mean, this is what really counts at the end, it was done at the expense of losing the transparency. So all these devices have been shown you, or with these diffuse scattering strategies are opaque. They are not transparent anymore like the ones I was showing in the beginning. And the reason for that is because diffuse scattering does not discriminate in wavelength. If I create disorder in my structure, although it can be done, it's a little bit sophisticated. If I introduce disorder in my structure, in principle it's very difficult that I will have multiple scattering effects for certain wavelengths and transparency for the rest. So I cannot preserve transparency. I just create white light at all. I create white light, it affects all wavelengths. Right? And this is what you see. These are experimental measurements of just a standard defined disolar cell and one with a diffuse scattering layer in which the transmitters only increase dramatically. Well, so how can we, is there any way that we can use to go back to this possibility of using integration and at the same time increase the efficiency of the device? Well, the answer is yes, and it's this one here. There are different ways to get color in nature. Color in nature. The most common one that we know is just by having dyes or pigments that absorb part of the spectrum, and the rest of the visible spectrum is reflected on material. This is what gives the sensation of color. However, there are colors. There is a source of color, fundamental phenomenon behind color that is not related to absorption, which is optical interference. So what we are looking at here is, in this picture, you're looking at 3 fields, each one with a very neat, very clear color, and in all cases you have exactly the same composition. The only thing that changes from one to the other is the structure of these of the material that compose them. So this is a cross-section of any of these, actually, could be one of them. What we did was to develop mirrors that were very robust optically, meaning that they can have very high reflectance, also chemically, thermally, and actually that reproduce, substitute the diffuse scattering layer that is commonly employed to get this boost in efficiency that is needed in the field. So the approach was based on creating nanoparticle multilayers. So we know that if we use nanoparticles, each layer in the system will be highly porous. And at the same time, it will have optical quantity, which these layers is absolutely transparent. Right? So even if you see all this disorder and all that, it's not affecting the optical properties in the visible range because the particles are very small. So I have the velocity that I need, and I have color. So this is, as I said before, the only difference between these three pictures here is the thickness of the layers that compose the structure. Okay? Well, I'm going to have this story short because we spent a long time trying many different approaches, and we collaborated with different groups to optimize these. But finally, it was demonstrated that you can actually have this structure. Well, okay, so what you're looking at here is again the cross-section of the diagram. But if you look at here, this thing, this part of the device now is a multi-layer structure with nanoparticles. Right? So this is a black mirror or a photonic crystal, a one-dimensional photonic crystal that is highly reflective. You have to think that with these mirrors here, we can get 78% reflected. While to get that reflected in the diffuse scattering layers, we need something like 4 microns on some of our nanocrystalline electrons. So we get the same reflectors with just maybe half micron. But not even to the spectral range, and we'll come to that later. So actually, we demonstrate that we will improve efficiency. Actually, you can also provide with color the device. So you get two things, right? You get efficiency enhancement and color controllable color. And we demonstrated this, as I said, with a number of collaborators in different research centers working with license. Well, this is the ID curve that we introduced the photonic crystal. So this is without, and this is with photonic crystals for thin films. The effect is dramatic. As the film gets thicker, well, the effect gets less important because we are absorbing more light to start with the reference. The reference is better. And this is actually the latest development we made in this field. What we wanted to prove actually is that you can really substitute the diffuse scattering layer by creating a multi-layer that was a white mirror. So we wanted to create a white porous mirror, but preserving a small spectral range so you can still see it. You can still have transparency. And this is what we did. I hope you can see it here. So this is one of the cells containing the multi-layer that we created, and you can see it too, actually. And this is a cell with a diffuse scattering layer, which is okay. You cannot read the letters in the back. This structure is not anymore periodic. In order to get a white reflector that covers most of the visible, you have to use an aperiodic structure, and you can see, you pay attention here, that when you have a gradual variation of the thickness of the layers in multi-layer, so you can reflect a very broad spectrum. And this is the performance that we achieved. So basically, this is a comparison. The green one is a diffuse scattering layer, it's a cell with a diffuse scattering layer, and the red one is a cell with these white porous mirrors that still allow you to get see-through cells. Right? There's always an advantage of using the diffuse scattering layer in terms of efficiency because it's better to reflect light in a really kind of something that you cannot get with the one-dimensional crystal. But this is maybe a small price to pay to preserve the transparency of the device. Well, all these developments we were publishing and patenting in the reverse order, and a company in Sweden became interested for this, and basically we licensed them most of the technology. This company is Exeger, and this actually becoming, I think, it become more and more important in the field. Is developing not only products based on our photonic crystal. This is a snapshot of their project. And this is a company based in Stockholm, and it grew from in a few years. Right now, they have 35 people working there. They have a final plan. They are creating the photonic crystal in large scale, and they have actually one of the main owners of this company today is Passat Glass, which is the main glass for building company in Northern Europe, which is actually interesting because I think this is basically it regarding the photonic crystal, and let me go back just a second. In all the approaches that I've been showing you, there's something that I didn't say at the beginning, but when you have a license type for a cell, there's the thing using transparency that is interesting, but there's another one, and it's that this is a cell that you can illuminate from both sides. So you don't get the same efficiency when you illuminate from the front and from the rear, but you get a pretty decent efficiency also when you illuminate from the back. This can be interesting if you have to place your cell like that, like for instance in the desert, you don't want it to get covered by sun. Or maybe, I don't know, separating desks between people working in an office. And all the approaches that I'm telling you, those that are based in diffuse scattering layers, which is here, or in the photonic crystal in the middle, well, kind of you do some stuff, you do the possibility to illuminate from the back. Because now you are blocking light in one direction. You're improving the absorption in the front direction, but you are blocking light in the rear direction. So that means that this is another thing that we were using when we introduced either diffuse or even the photonic crystal that we were proposing. So we started thinking about ways to improve absorption, improve light harvesting, but preserving this functionality of the cell. So is there any way? And the answer is texture surfaces, which I mentioned at the beginning. What is that? Okay, well, if I have a texture surface, and maybe I should actually show this first. So this is basically what we were proposing. This darker gray would be our titanium oxide film, and what we were proposing is to butter it. So when you butter that, you create an optical diffraction rate in your light. And the good thing of a surface rating is that it will provide you diffraction with reflection modes and transmission modes. So when you illuminate from this side, you take advantage of the light that is diffracted through these reflection modes. So these are optically diffracted modes in reflection. And when you illuminate from the back, you can take advantage of the light that is reflected by diffraction again, but in this case, you take advantage of transmission mode. So no matter how you illuminate the structure, you always get longer optical paths for the light that is coming inside. And this, we can prove that by actually using a simple, it's very developed, so it's simple for everybody to copy, using some lithography. You know, it's the technique that George Weinstein developed more than a decade ago. And basically, we started with a commercial diffraction rating, super cheap diffraction rating. We just made a copy in PMS, hard PMS. And then we stamped our titanium electrode. And this is what we got, right? This is the profile you get in the IFM. So you reproduce pretty good the replica, the replica. Obviously, because you are buttering something that is not crystalline, you get a little bit of roughness in this picture. But it's a pretty decent replica, and actually you can see this is the diffraction you get from your titanium. And if you check the efficiencies, what you observe is that obviously when you illuminate from the front, the diffuse scattering layer, which is this ivy curve here, corresponds to that, is much better than introducing this surface texture. But when you illuminate from the back, the diffuse scattering layer drops dramatically, and your texture surface still performs. So if you are interested in double-sided illumination, the diffuse scattering layer is not an option, and not for some crystal, you have to go for something like that. And a small texturing, which is actually very simple to do, which is just something, it's not a sophisticated technique we're proposing, might allow you to increase a little bit the absorption, right? For both, for bifacial, let's say. Okay, so I'm going to get to the last part of my talk. I'm going to talk about perovskite solar cells and what can we do there. And I have to admit that there's not much you can do with perovskite solar cells in terms of optics, because we have very little space. Perovskite solar cells usually have between 300 and 500 nanometer thick layers of the absorbed And also because it already absorbs electric light, it has a very high optical extinction constant that makes it complicated to improve efficiency. And actually, I'm not going to talk really about improving the efficiency, but something else. So our story with this cell, and I'm briefly going to introduce it, because probably you already have seen these conferences and things like that. But this is the results I'm going to present were a collaboration between the group in Hernan Miguez in the University of Oxford and our group in Sweden. He approached us like a year and a half ago and asked us if it was possible to change the color of the perovskite solar cell. The motivation was that when he showed these to the architects, because they are very interested in dealing with the robotics, they didn't like it. This brownish color is not attractive for people working in architecture. They asked him that. He asked, can we get that in different colors? Can we do something like that? So, this was our motivation. And actually, well, you see this is the device, and this, I just want to highlight that this is, again, the FTO. This is a thin compact layer that you can just see as a dark line here. This is a scaffold, so the cell itself produces a porous, in one of the configurations, is making use of a porous titanium oxide, maybe some other oxides, this is infiltrated with perovskite, and this is a capping layer, an another layer of perovskite, this white material. The black one is the whole transporting layer, and this is the gold content. Right? So this is the basic structure of a perovskite. And when Henry asked us how to introduce color here, we started analyzing these. But actually the first thing we did was a full optical description of the basic device, which hasn't been done, hadn't been done at the time. We published actually that, and it was released with 4 other papers that also were, calculating or describing all the optical features of these devices. We knew that people had tried before to change the look of the cell, and one of the approaches was developed in Korea, the group of Sunny Cell. And what they did is, okay, if we want color in the perovskite solar cell, let's change the composition. They moved from the methyl-ammonium electron-like perovskite that I just presented to a perovskite in which you were gradually changing the composition, combining bromine and iodine, methyl-ammonium, bromine, methyl-ammonium, iodine. So this, by doing this, you are changing the matter, which you're basically changing the absorption of your perovskite. So this is why you can get a different color for a certain range of ratios between bromine and iodine. And this color that it's never green or blue, it's always orange, yellowish. Well, you get it at the expense of getting a 4% feature. Right? This is what we were getting. Then there are other ways to change the look of the cell, which were actually developed by the same Henry Miguez or Panchromatic that were based on reducing a lot the thickness of the perovskite layer and of the metal content. So you can get this transparent solar cell. So what we have examples of, again, the relevance of the optical design, right? Because it gives you a whole new range of possibilities of integration, right? Like making this transparent or color. What they were interested is in having the full color palette, and when we started, there was no method to get that. So what we proposed was the following. It was not possible to put a photonic crystal in the back, as we did with the dye-sensitized solar cell. If you do it like that, well, you simply don't get anything, because the perovskite absorbs everything before it reaches anything in the back. So we had to, and we knew we were going to use it because of that, to put it in front, right? So we integrated it. What we did was to substitute the scaffold, the titanium oxide scaffold, by a photonic scaffold. We introduced a multi-layer that was porous, as I said before, in the place where you would find normally the mesostructure scaffold. But what happened? Even when we had a lot of experience with these materials, it took us a year to find the right one. And the reason was because if you use just the porous photonic crystals we had developed before, when the perovskite infiltrated that structure, it was too much. It was too much perovskite. So you were losing color. The photonic crystal was not anymore color. Right? The perovskite was absorbing everything. So we had to find a way
goes from one layer to the other. So we have full connectivity of the perovskite inside the device, even when it is a very low protein threshold. This is the way the device looks. If you look at the cross section, so you see the multi-layer structure here. Right? This is the capping layer of perovskite. This is the FTO. Sorry, but actually, and this is what we got. So we were able to obtain devices that can be violet, blue, green, orange, red, without losing, well, obviously we're losing efficiency, but preserving efficiency, so to say. In any case, much more than what was achieved before. So we have a full color palette now. Now each device is completely different in terms of the optical response, as you can see, obviously. But, as we go to this one here, if you look at the external quantum efficiency, this is a proof that we are not modifying the band of the material. We are always working with the material monitor material for the perovskite solar cell, but we have completely different optical response. You can tell clearly in the external quantum efficiency the price that you are paying, right? Because we are decreasing the external quantum efficiency in those regions for which we are doing this reflection. We did that designing everything with the model we have created for the solar cells, and maybe I have no time to get into that, but there are very interesting things that you can learn from this model. You can actually see exactly each wavelength how it is distributed inside your device. And you can determine all parasitic absorptions and productive absorptions, and actually now you can do the internal one. Okay, so this is the summary of this work that I just presented. The most important thing basically is that the devices we were making were as stable as all the devices in the field, so the scaffold was as good as any other scaffold, but you can get all these colors, right, which are pictures of the with a microscope. This is why it's a little bit smaller scale. And actually, you see what happens with efficiency. So for blue cells, we could preserve around 8% efficiency, having a reference of a 10% efficiency. Right? So the blue cell was at 8%, and basically you can get from blue to orange keeping almost between 6 and 8%, which is, I know, much lower than the record that you can get in the first slide. But you can get that systematically, and also it competes very well with any other technology that allows you to introduce color in a photovoltaic device. So I think this can be an interesting, very interesting for the future, for being integrated for photovoltaics. Well, and as you can see, there's no a big effect on open circuit photovoltaic fill factor, except in the case of the red. The reason why the red is complicated is because if you want to have record, you need to put feeder layers, and that starts introducing problems in the perovskite connection. So you cannot make them too big. Well, finally, I'm not finally, but I'm very close to the end. I don't know how much time I have left. Maybe 10 minutes, 5 minutes. So I said that I was going to discuss periodic expansion in perovskite. This is what I did. As you can see, we didn't improve it. We provided the property that they can have. As I said before, for time sensitized ourselves, after our calculations, well, we cannot recommend use microparticles. And I thought I was going to find the same thing with perovskite. But with perovskite, it comes out that if you do a very detailed analysis of it, metal particles can help you to improve efficiency when you have thin layers and 200 nanometers. They're up to 300 nanometers. So these are actually the type of thickness that you can find in a perovskite solar cell. So I'm not going to explain everything that I put in this slide because it's too long, but basically what you see here is our estimation of is what happens with absorption. So this is a map of absorption where I have a gold particle inside a perovskite layer surrounded by a spirometer and glass layer. So there's a clear effect, positive effect of the near field around the gold and around the gold particle, and also the this is not the electromagnetic field, this is absorption. So you have a contribution of absorption, to increase absorption both by near field effects and by scattering effects. And actually, we use this parameter, which I like a lot, it's very revealing, which is the solar spectrum weighted integrated absorption. So when I don't care anymore about the exact shape, I integrate everything, taking weighting it with the solar spectrum. And you can get efficiencies up to 6% better in things of 300 nanometers, so these the news are not bad. And actually, if you go to smaller things of 200 nanometers, you can get up to, you can see this here, you can get up to a 10% improvement in absorption. So it's something pretty terrible. And finally, at this time, it's really final. I have told you about our work with solar. Actually, our main project in the group is this one here, which is the development of flexible optical materials. And I brought it here because I haven't mentioned organic solar cells and stuff. The reason is that every time we try to do something with organic, and I would say that every time I read someone is trying that there is something else, I think there's very little to do that. So it's almost impossible to work with a material that has such a short quantifier diffusion length, and therefore they have to always deal with extremely thin data. So it's almost impossible to work under these conditions, I would say. However, people in the field, and I saw yesterday, the day before yesterday, I saw by doing an answer, which is one of the gurus in the field of OP, talking about what they are doing now. What they are doing is to introduce diffuse scattering layers at the very back of the cell, but not integrated inside, but on top of the cell. They create this very highly diffuse layers so they can have some light back into the system. And I think what we are developing in that regard can also be helpful because we develop these flexible mirrors in which we combine two things. We combine the higher electric contrast and therefore very high reflectors that we make in the organic material, but the mechanical properties of volume. And we do that by creating volume structures, different kinds, as you see here or here, that are particle material actually before. And we integrate that in the polymer so that we can get a self-expanding film, which I think is the highest reflectance, color reflectance that you can get nowadays. And in this sense, I think this can be used also to improve the efficiency of OPE in the same way that it's been done. So this is my group, and I just wanted you to, this is another picture. This is why there are more names here than people in the picture, but basically the work I have shown you was was performed by my previous PhD students, Silvia Corobredo and Carmen is here, and all the work with the perovskite solar cell has been done by Dr. Mauricio Calvo, Dr. Gabriel Lozano, who is the one in charge of the simulations, and the PhD student Miguel Anaya. And with this, I thank you for your attention.